Look at this top-down view of a meandering river aggressively eroding its banks and shifting its course over a floodplain. To understand why this lateral migration happens, we have to start at the river's origin point. In this upper reach, the terrain dictates the hydraulics. The steep gradient generates high-velocity flow, giving the water enough kinetic energy to actively scour and degrade the bedrock channel. As the river descends and exits the foothills, it enters the alluvial plain. Here, the terrain flattens out. The flow velocity drops significantly, and the river no longer has the energy to carry its heavy sediment load, causing an aggrading or rising bed as material settles. To manage this constant deposit of sediment while still moving water downstream, the river enters a state of dynamic equilibrium. It begins to meander. High-velocity flow swings to the outside of the curves, scouring away the outer banks, while slower water on the inside curves drops sediment. The river balances itself perfectly through this continuous lateral movement. But the problem is, human infrastructure is fixed in place. This schematic shows a stationary bridge and canal intake near an active river curve. Watch the outer bank erode. The high-velocity flow shifts directly into the bridge abutment, creating a zone of structural failure and completely altering the hydraulic approach angle the canal relies on. Engineers counter this natural migration using river training, the deployment of physical structures to constrain the flow and force the river into a stable alignment. You cannot use the same structure for every scenario. Civil engineers strictly divide these interventions based on the specific seasonal flow regime they need to control: high water, mean water, or low water. This tripartite framework defines the specific engineering objectives for the channel. We can see exactly how these definitions are tested by looking at the explanation for question 47 from this gate prep material. High water training is built for maximum discharge, ensuring floodwaters pass safely through the reach without inundating the surrounding plains. Once the flood risk is mitigated, the priority shifts. Mean water training handles the daily mechanics of the river, aiming to efficiently dispose of suspended sediments and make the overall river course stable. Then, during the drag season, the flow drops and a new problem emerges. Low water training focuses entirely on depth, concentrating the minimal remaining flow to provide sufficient draft for navigation. When distinguishing these on an exam, look at the target variable. Mean water targets sediment and bank stability, while low water strictly targets channel depth. Knowing the theoretical objectives requires understanding how to physically execute them in the channel. Look at this technical diagram of temporary diversion headworks, focusing on the structures in the lower half. You can see the primary tool for localized hydraulic manipulation, the spur or groin. These project outward from the solid banks directly into the active river flow. These structures act as shields. They deflect the high-velocity current away from the vulnerable, eroding outer banks. By pushing the main current toward the center, the spurs create localized, low-velocity, dead water zones immediately downstream of each block. Because the water velocity drops some sharply in these pockets, it loses its transport capacity and drops its suspended sediment load. This induced silting reclaims the land, locking the original riverbank securely in place and successfully executing a mean water training objective. We can use that same structure during a dry season, where the goal shifts to low water training. By extending spurs from both banks, we artificially constrict the channel width. The existing low discharge is forced through a smaller area, increasing central flow velocity. That concentrated, faster-moving water begins scouring the center of the riverbed, naturally carving out a deeper channel. This newly excavated depth provides the necessary draft for ships to safely navigate the river, even when overall water levels drop. A single structural tool manipulates the hydraulics to achieve completely different training objectives based on its length, angle, and the resulting channel constriction. Competitive exams will test your ability to look at a physical river condition and correctly map it to the corresponding engineering solution. Here is the matrix you need to evaluate these problems. When the problem is extreme discharge and the threat of flooding, the objective is high water training, and the structural solution is a longitudinal embankment. When the problem is heavy sediment load and aggressive bank meandering, the objective is mean water training, using spurs to induce localized silting. When the problem is shallow draft during dry seasons, the objective is low water training, executed by constricting the channel width to force bed scour. River training is a fluid mechanics equation. Engineers manipulate channel width and local velocity to dictate exactly how the river behaves. When facing multiple choice questions, rely on these strict objective-based definitions rather than intuition. By calculating and applying these specific structural interventions, civil engineers force the massive, chaotic energy of an alluvial river into a predictable and economically vital asset.